Today we're going to be talking about section 1.5, solution sets of linear systems. So let's start by talking about a specific kind of linear system and take a look at what its solution sets look like. So a system of linear equations is homogeneous if it can be written as AX equals 0. So if we think about what this looks like in terms of an augmented matrix, it means we'll have a matrix with whatever our coefficients are in it, and then the augmented piece of this is just going to be a column of zeros. This is what a homogeneous system of equations looks like. Okay, we talked in the first week about how any system of linear equations can either have no solution, one solution, or infinitely many solutions. Under what situation do we have no solution? That's if our system is inconsistent. So if we have something that looks like 0 equals something non-zero like 5, that's when our system is inconsistent. In a homogeneous system of equations, that's impossible because our right-hand side of that equation is always going to be 0. So even if we have a row of zeros at the bottom, that's okay because we'll get 0 equals 0 instead of 0 equals, say, 5. So this will always be consistent no matter what. So it is impossible to have no solution. Okay. So if we always have to have a solution, what would that solution look like? Well, if we think about this homogeneous system of equations as a vector equation, then what we're really doing is we're trying to find weights for every column of A so that we equal 0. Well, if all of our weights are 0, then it doesn't matter what A is, our system will equal 0. This is called the trivial solution. So we will always have a solution to this system, and in fact, the solution x, the vector x equals the vector 0 is always going to be a solution to this system ax equals 0. This is because 0 times anything is 0. All right, what does it look like if we have the trivial solution, if we have a system in which every single one of our variables equals 0? Well, if that's our only solution, then what that would look like is we'd have to have a pivot position in every spot that we can. So for instance, we would have a 1 in our first variable, we'd have a 1 in our second, a 1 in our third, and so on, to tell us that every single variable is going to equal to 0. Now, if we want something that is a solution that isn't the trivial solution, if we want a non-trivial solution, we already know the trivial solution has to exist. So the only way to also have a non-trivial solution is if we're in our last category, the one with infinitely many solutions. And the only way we can have that is if we don't have a pivot position for every variable. So in other words, if we have a free variable. So we only have infinitely many solutions if we have a free variable, and we can only have a non-trivial solution if we have infinitely many solutions. So let's just go ahead and write that up. If we have infinitely many solutions, then we must have a free variable, and that's the only way to get a non-trivial solution. All right. Great. So we now have talked about what our solution sets look like, and we've talked about basically the only interesting situation is if we have a free variable. So let's actually look at an example in which we have this. So let's say we have a system that's augmented matrix looks like 1, minus 3, minus 4, minus 3, 9, 6, and minus 1, 3, 2. Well, what's the first thing we want to do when we want to find a system of equations or a solution set to the system of equations? We go ahead and put it in reduced row echelon form. I'm going to trust that you all know how to do that by now and can do it on your own. If we put this in reduced row echelon form, this ends up looking like 1 minus 3, 0, 0, 0, 1, and a row of zeros on the bottom. The nice thing about homogeneous systems of equations is that no matter what row operations you do, this column is always going to stay 0. All right, let's take a look at what our solutions look like here. This first row looks like x1 minus 3x2 equals 0. This equation says x3 equals 0, and this equation says 0 equals 0. This doesn't really give us any information beyond the fact that this is a consistent system. And the way that we have written up our answers in the past is, let's write them up so that we see what x1 equals, we see what x2 equals, and we see what x3 equals. In this case, x1 is going to equal 3x2, x2 is free, and x3 is 0. Now, we can write this up in a more concise way if we want to think of our solution set as a vector, a solution vector. So if we think of our x solution set as a vector, our vector looks like x1, x2, x3, and we can go ahead and fill in our answers that we just wrote down into this vector. So x1 equals 3x2. x2 is free. How do we write this down? We write this as x2 equals x2. What this means is x2 can equal anything because, of course, x2 is always going to equal itself, and x3 equals 0. We can take this a step further by saying, hey, look, we have an x2 in our vector. Let's go ahead and factor that out. So we'll take out the x2 and we'll say, all right, how many copies of x2 did x1 have? It had 3 copies. x2 had 1 copy of x2, and x3 had no copies of x2. So this is our solution set. This way of writing our solution set is called parametric vector form. Oops, ran out of space there. Parametric vector form. And it's the most common way to write up our solution sets. Geometrically, what does this look like? We have infinitely many solutions, and our solutions all live on the z-plane because our third variable equals 0. So let's go ahead and project this down onto the z-plane because it's easier to draw in 2 dimensions. We have 3, 1 as our main vector here. And then this x2 says we can take any scaling of that vector that we want. So we can plug in any constant for x2, scale that vector in any way we want, and that will still be a solution, which means that our solution set looks like this entire line. So we have infinitely many solutions and they all lie on this line. So this is an example of what happens when we have one free variable. Let's take a look at what happens when we have more than one free variable. So I'll go ahead and give you this example already put into reduced row echelon form. So let's say we have a system that in reduced row echelon form looks like this. So if we write out what our rows tell us, this row tells us that x1 plus 5x2 minus 3x3 equals 0, and x2 and x3 are going to be free. So let's put this in parametric vector form. We want our solution vector x, which again has 3 variables, x1, x2, and x3, because we have 3 columns in our coefficient side of our augmented matrix. And we can write down what each of these equals. So x1, if we solve for x1 up here, we want to subtract off our 5x2 and add on our 3x3. So this looks like minus 5x2 plus 3x3. And x2 is free, so it just equals itself. And x3 is free, so it just equals itself. Now, if we want to factor out the x2 and x3, there are 2 variables we need to factor out. So let's break this up into 2 pieces. So first we have our x2 piece. And what is this vector that x2 is multiplied by? Well, x1 has minus 5 copies of x2, so we'll put a minus 5 here. x2 has 1 copy of x2, and x3 just equals itself, so it has no copies of x2. Similarly, we'll then add on to that how many copies of x3 each of these have. So x1 has 3 copies of x3, x2 has no copies of x3, and x3 has one copy of x3. So this is what our solution set looks like. And again, this is parametric vector form. This is our parametric vector form with solution sets. You'll notice that x2 and x3, again, can be anything. So that means that any linear combination of these two vectors is a solution. So another way of writing the solution set is it's the span of these two vectors, minus 5, 1, 0, and 3, 0, 1. And geometrically, what does that look like? It means that our solution set is going to be anything in the plane that is defined by these two vectors. You'll notice that the solution set for this example is two-dimensional, it's a plane, whereas the solution set for the previous example was one-dimensional, it was a line. This is entirely dictated by the number of free variables. So the number of free variables that you have is going to be the same as the number of vectors that we span. So in this case, we had 2 free variables, and our solution set was the span of these 2 vectors. And that's the same as the number of dimensions of the geometric set that shapes our solution set. Right. So we've pretty much explored what homogeneous solutions look like, or solutions to homogeneous equations. Adjacent to that is non-homogeneous systems of equations. So a non-homogeneous system of equations is a system that looks like ax equals b, where b isn't the 0 vector. So non-homogeneous systems are systems that aren't homogeneous, shockingly enough. So it's important to note that our solution vector b can have zeros in it, it just can't all be zeros. But luckily, we solve these in pretty much exactly the same way as we would solve homogeneous systems. So let's take a look at an example. Again, I'm going to go ahead and give you this one already put in reduced or echelon form. But if you got a system that wasn't in reduced or echelon form, you would just do our row operations as you know how. Okay, so let's see. Here's our system, and we've gotten it into reduced row echelon form, and it is not homogeneous because our B here has a 0 in it, but it is not all zeros. It is consistent because this last row just gives us 0 equals 0. So this tells us that x1 plus x3 equals minus 5. This tells us that x2 plus 2x3 equals 1, and this equation just tells us that 0 equals 0. So we're going to write up our parametric vector form solution in exactly the same way as we did with homogeneous systems. So we want a solution, again, with 3 variables, x1, x2, and x3. And then we can just fill in what each of these equals. So if we solve for x1 using this equation, we see that x1 equals minus 5 minus x3. X2 equals 1 minus 2 x3, and x3 just equals itself because it's a free variable. And again, we want to factor out this x3, but now we have some constants to take care of as well. So we'll go ahead and make a separate vector that's made of the constants. So we've got minus 5 is the constant for x1, 1 is the constant for x2, and 0 is the constant for x3. Notice that this looks an awful lot like our vector b here. And then we can factor out x3. And again, x1 has minus 1 copies of x3, x2 has minus 2 copies of x3, and x3 has 1 copy of x3. So here's our parametric vector form. You'll notice if we had this exact same system, but instead of being non-homogeneous, it were homogeneous, so this were all zeros, then this vector right here would just be the 0 vector, but we'd still have our same x3 times this same vector. What this means is if we have a non-homogeneous system, basically all we're doing is we're taking our solution set for our homogeneous system, and then we're translating it by that vector b. So for instance, if we had a homogeneous system here, our solution set would look like a line along the vector minus 1, minus 2, 1. By having it as a non-homogeneous system, we're just picking up that line and translating it by -5, 1, 0. But our solution set still looks like a line. Great, that's all I have for you today, and I will see you in class.